Hello everybody, my name is Ethan. Welcome back to the channel where today we are hopping back into the machine learning course on Codecademy, and today is a very exciting day as we are going to the intermediate machine learning section of the course. In the previous video, we finished out the software engineering for machine learning chapter, which included a lot of different things, including Git, the command line, and some other stuff like bash scripting. So if you missed any of that, it's going to be in the previous videos that came before this one in this playlist, so make sure to go check them out if you missed it. But I am extremely excited today to get into some of the content in this. Right now it's telling me that we're about 80% of the way through the course, so it's been a long time coming, and I'm really excited and enthusiastic about getting back into it and getting into some actual machine learning. Again, in this previous chapter it was kind of just more software engineering based stuff, so it's gonna be fun. All right. Let's kind of get into this course. We obviously have always this little starting thing anytime we start a new chapter where it kind of details you, why did we build this machine learning course? What will you learn? And then again, who are the classmates in the forums and stuff like that. Most importantly is obviously going to be this what will you learn section, so we'll detail that really quickly. We're going to learn how to apply and evaluate intermediate supervised learning algorithms like SVMs and naive Bayes. The best ways to improve and tune ML models with regularization and hyperparameter tuning, and how to leverage the power of ensembling methods like bagging, boosting, and stacking. All right. Pretty excited again. Hopefully you guys are too. I am super ready to learn. All right, introduction to Bayes' theorem. So if you don't know what Bayes' law is or Bayes' theorem, this is something that is a pretty big stats concept. So making sure that you're familiar with this is probably a good idea. In this lesson, you will learn about Bayes' theorem. Bayes' theorem is the basics of a branch of statistics called Bayesian statistics, where we take prior knowledge into account before calculating new probabilities. This allows us to find narrow solutions from a huge variety or universe of possibilities. British mathematician Alan Turing used it to crack the German Enigma code during World War II, and now it's used in machine learning, statistical modeling, and A/B testing, as well as robotics. By the end of the lesson, you'll be able to solve simple problems involving prior knowledge. Before we learn this theorem, we'll need to review independence and conditional probability. So here we have the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. Independent events. So the ability to determine whether two events are independent is a very important skill for statistics. If two events are independent, then the occurrence of one does not affect the occurrence of the other event. Here are some examples of independent events. I wear a blue shirt and my coworker wears a blue shirt. I take the subway to work. I eat sushi for lunch. The New York Giants win their football game and the New York Rangers win their hockey game. If the two events are dependent, then when one event occurs, the probability of another event occurring changes in a predictable way. So here's some examples. If it rains on Tuesday, I might carry an umbrella on Tuesday. I eat spaghetti, I might end up with a red stain on my shirt. If I wear sunglasses, I might be going to the beach, right? A certain family plans to have 3 children. Is the event that the couple's third child, a girl, independent of the event that the couple's 2 first children are girls? Save your answer, independent or not independent to third child. I would say that this is most likely an independent event, just because you don't know for sure if you're going to be having a girl or a boy, depending on what happens with the pregnancy and stuff like that. So definitely an independent event. So conditional probability is the probability that 2 events happen. It's easiest to calculate conditional probability when the 2 events are independent. For the rest of the lesson, we'll be using the statistical convention that the probability of an event is written as P event. So that's very common phrasing or syntax when talking about probabilities in regards to syntax. You'll see it often, almost always written as probability of an event. So if the probability of event A is P of A and the probability of event B is P of B, and the 2 events are independent, then the probability of both events occurring is the product of the probabilities. So it's just A times B. The upside down U symbol means and. And so A and B means the probability that both A and B happen, right? So for instance, suppose we're rolling a pair of dice and we want to know the probability of rolling 2 6s. Each die has 6 sides, so the probability of rolling a 6 is 1 in 6. Each die is independent, i.e. rolling 1 6 does not increase or decrease our chance of rolling a second 6. So we take the probability of rolling a 6 and the probability of rolling another 6, which is 1/6, and another 1/6, and we multiply them. So it would be 1 in 36, right? All right, this week there is a 30% probability that it will rain on any given day. At a certain high school, gym class is held on 3 days out of the 5-day school week. On a school day, what is the probability that it is raining and the students have gym class, right? So we're going to say that the probability of having gym class is, of course, 3 in 5, right? 3 out of 5 days we're having gym class. And we're going to say that the rain is a 30% chance, or 3 in 10, right? So these events definitely seem to be independent, right? Just because we have gym class doesn't mean it's going to be raining that day. So what I will do is I'll multiply 1 divided by, or I should say 3 divided by 10. And we're going to multiply that by the probability that we have a gym class, which is 3 divided by 5. And when we run this, we're going to save it out and we'll save our answer. And then we can, of course, because it is a Python, we can print this out and see. Looks like there's an 18% chance that it will rain and it will be a gym class, right? So, all right, let's test for some rare disease. Suppose you're a doctor that needs to test if a patient has a certain rare disease. The test is very accurate. It's correct 99% of the time. And the disease is very rare. Only 1 in 100,000 patients have it. You administer the test and it comes back positive. So your patient must have the disease, right? Not necessarily. If we consider the test, there's only a 1% chance that is wrong, but we actually have more information. We know how rare the disease is. Given the test came back positive, there are 2 possibilities. 1, the patient had the disease and the test correctly diagnosed the disease. Or 2, the patient didn't have the disease and the test incorrectly diagnosed that they had the disease. What is the probability that the patient had the disease and the test correctly diagnosed the disease? So, we can do this by creating a new variable called disease, if we can spell, and correct. And we're saying that the thing is accurate 99% of the time. So we can do that by doing 99 divided by 100. That is the probability. And we're saying, okay, yes, it was disease. It was correctly proposed, but it's also 1 in 100,000. So we're going to also multiply this by 1 in 100,000, right? P disease. I think I spelled, yep, I did. Spelled it wrong. I thought I got it wrong, but I spelled it wrong. All right, what is the probability now? So we got that one. Let's print it out just to see what it is. P disease and correct. Looks like it's a very, very small number, right? E to the negative 6. We can create this new one now, which is no disease and incorrect. So we'll set that the test was actually incorrect. So again, it was correct 99% of the time. So we can see that 1 in 100, right? And then the patient does not have the disease. So what is that probability? Well, that's obviously going to be 999,999 divided by 100,000, right? So when we do that, we'll find that probability. We're going to print both of them, right? So we'll print P, no disease, and incorrect. So now we can see, oh, it's much more likely that our test was incorrect than they actually have the disease, right? So we can see this is an extremely small number. This is just about 1/10 of 1%, which is obviously still rare, but it's way more than this number here. All right, Bayes' theorem. In the previous exercise, we determined 2 probabilities. One, the patient had a disease and the test correctly diagnosed the disease, roughly 0.00001. And the patient did not have the disease and the test incorrectly diagnosed it, and it's roughly 0.1, right? 0.01, so about 1%. Both events are rare, but we can see that it was 1,000 times more likely that the test was incorrect than that the patient had this rare disease. We're able to come to this conclusion because we had more information than just the accuracy of the test. We also know the prevalence of the disease. In statistics, if we have two events, A and B, we write the probability that event A will happen, given that event B already happened, as probability of A, tall bar, which we say is given B. In our example, we want to find the probability that we have the rare disease given that we had a positive result. In other words, we want to find the probability that the patient has the disease given the test came back positive. We can calculate the probability of A given B with Bayes' theorem, which states probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. So in this case, we'd say that the probability of getting the rare disease given that we had a positive test result, or not getting the rare disease, but having the rare disease, given that we had a positive result, is equal to the probability of getting a positive result, given we had a rare disease, times the probability of a rare disease divided by the positive result. So it is important to note that on the right-hand side of the equation, we have the term probability of B given A. This is the probability that event B will happen given that event A has already happened. This is very different from probability of B or A given B, which is the probability we're trying to solve for. The order matters. So first we're going to calculate the probability of a positive result given rare disease, or the probability of a positive test result given the patient really has this rare disease, right? So I am going to take just a quick peek at the hint, make sure I'm doing this right. So we want to first, again, save our answer to P positive given disease, right? We'll set this equal to something. The test is 99% accurate given the fact that the patient has the disease. We know there's a 99% chance, right, that it will return a positive result. This is exactly, so it should look like 99, right? So does that make sense? Obviously, as the fact is, we're saying, given they have the rare disease, right? Just given that they have it. They are the 1 in 100,000. What is the probability that the positive results will occur? Well, we already know that a positive result happens 99% of the time. So we're saying that this is 99, right? All right. We can run this now. All right, what is P rare disease? So we know that this one is one that we already knew. It's that 1 in 100,000, right? That one is the 1 in the 100,000. We already saw that earlier, so we know that one. Now we need to compute the denominator. We'll need to find the probability of a positive result. As we discussed previously, there's two ways to get a positive result. The patient had a disease and the test score diagnosed the disease. The patient had the disease and the test correctly diagnosed the disease. And the second way is the patient didn't have the disease and the test incorrectly diagnosed that they had the disease. So again, these are two positive results, right? Using these two probabilities, calculate the total probability that a randomly selected patient receives a positive test result. Save that answer to a variable called P positive. P positive. So the way that I would do this is I would just multiply probabilities, right? So what is the patient, if the patient has the disease and it tested correctly, that obviously is this one up here. So we can also just do P positive given disease. And then we can multiply that by a new one, which is the patient didn't have the disease and it incorrectly diagnosed, which if we remember, that is the 999,999 out of 100,000, and we'll multiply this. I'm going to use another set of brackets just to make sure that we can see everything. And then it's given that it was an incorrect test result, which is 1 in 100, right? We're going to save that now to an answer called P positive. And we'll see the probability that the patient had the disease and the correctly diagnosed. Because it's 1 over. So we can, 1 over. Let's see, the probability that the patient had the disease and correctly diagnosed the disease is this number, which is 100,000. Probability the patient A plus B. Okay. If we do it in plus instead, what happens? Okay. I wish they would go through this just a little bit more, but that's okay. We want to see the probability that the patient had the disease and test correctly diagnosed the disease is 1 over 100,000 times 99. Where we're getting that, I'm not really sure. 1 over 100,000 times 99. 0.99 actually is what it's saying here. And then the probability that, so it's saying it wants this, right? 999,999 divided by 100,000 times 1, or 0.01. We knew that it was A or B, right? So there are 2 ways to get a positive result. The patient had the disease. Patient had the disease and the test correctly identified it. So that should be right now. Substitute 3 values in for the Bayes law. So we can say P disease given is equal to I'll do this first. P positive given disease times P disease divided by P positive. Print this. P disease given positive. And it's looking like it was very unlikely that the patient actually has the disease. All right, cool. Spam filters. Let's explore a different example. Email spam filters using Bayes' theorem to determine if certain words indicate that an email is spam. Let's take the word that often appears in a spam, enhancement. With just three facts, we can make some preliminary steps towards a good spam filter. Enhancement appears in just 0.1% of all non-spam emails. Enhancement appears in 5% of spam emails. Spam emails make about 20% of total emails. It's asking us, given that email contains the word enhancement, what is the probability that the email is spam? All right, so in this example, we're dealing with 2 properties, right? So the first property is P enhancement, the probability that the word enhancement appears in an email. P spam is the probability that an email is spam. Using Bayes' theory to answer our questions, we want to calculate A given B, but what are A and B referring to in this case? Say the string spam to the variable A. So we'll say A is equal to the string spam, and we'll say B is equal to the string enhancement. So now wants to calculate the probability of spam. P spam. So probability of spam is the probability that that an email is spam. So the probability that an email is spam is roughly 20% is what it looks like here. That's what our third fact states, right? Yep, so I would say that it is 1 in 5. Nice. All right, what is the probability of enhancement given spam? Save your answer to P enhancement given spam. So we can say P enhancement given spam. And we're going to have to set this equal to something. So what is P enhancement given spam? We're trying to answer given enhancement, what is the probability of spam? But given this is going to be, first, what is the probability of spam? We've already given that. So given that we have, it is confirmed spam, what is the probability that enhancement ends up in our chat box? Well, it says up here in rule 2, in spam emails, enhancement appears about 5% of the time. So we can say that the probability of enhancement given spam is going to be 5%, or just about 1 in 20, right? And that is correct, right? So we can continue. We want to know the overall probability that any email, spam or not spam, contains enhancement, because we know the probability of enhancement occurring in both spam, 0.05, and spam emails, 0.001 emails. We can use a weighted average to calculate the probability of enhancement concurring in an email. So this is going to be amazing. Oh my God, my nose is a little itchy today, guys. Sorry about that. So we want to save the probability of enhancement. It wants me to use this formula. So let's read over it just one more time. We want to know the overall probability that any email, spam or not spam, contains the word enhancement. Because we know the probability of enhancement occurring in both spam and non-spam, we can use a weighted average to calculate the probability of enhancement occurring in an email. So we'll take the probability of enhancement given spam times the probability of spam plus the probability of enhancement given not spam times the probability of not spam. So this first one's really easy, right? So it's just going to be P spam times P I don't know why I keep saying enchanted. Enhancement given spam. That's the first one. That's pretty easy. The second one, we're going to have to do a little bit of calculating for. If we know the probability of spam and not spam, they're going to be exclusive, right? So they're going to add up to 1, right? So I'm going to say that the probability of not spam is going to be 4 out of 5. So I can just quickly do 4 divided by 5 and multiply this by the probability of an enhancement given it's not spam, right? And we also have this, right? So this one was specified in step 1, right? If we go back up to, or I should say fact 1, the word enhancement appears in just 0.1% of non-spam emails. So we can say that probability of enhancement given not spam is going to be that number of 0.0001, right? Because it's, well, actually, it might just be 1. No, it's just 1. Yeah, there we go. That should be correct. Perfect. All right, now that we know probability of spam, probability of enhancement given spam, and probability of enhancement, we have all of our parts and pieces to plug into Bayes' theorem. So we can now actually create that here. We can do P spam I keep doing it, enhancement, and set it equal to, again, we'll start off with the probability of P enhancement given spam, and we're multiplying that by the probability of A, which is the probability of spam. So we do P spam. And then we're going to divide that by the probability of B, or probability of enhancement, which in this case is P enhancement. It's like my fingers are not coordinated today. We can now print this out. Print P spam enhancement. So it's saying that what is the probability? We've kind of solved our question. The question that we got was, given that an email contains the word enhancement, what is the probability that the email is spam? Well, what we found was that if our email contains the word enhancement, there is a 92% chance that that email is spam. So, nice. All right, review. In this course, we learned several new definitions. The two events are independent if the occurrence of one event does not affect the probability of a second event. And if two events are independent, then the probability of A plus B, or A and B, is probability of A times B. And Bayes' theorem is the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. All right, up next. We got a little bit of stuff towards machine learning, a little bit more towards math. Always like math. So we can continue on here. And it looks like we're kind of dipping into something else. Yeah, we kind of went through Bayes' theorem. I don't want to go too fast through it, so I think that's where I'm going to end the video. It's going to be a short one today, and that's okay. I'm still going to be excited, and I'm probably going to record some more videos just today, just because I want to get them done, and I'm happy and really excited to do them. So if you did enjoy the video, please be sure to give a like, subscribe, and I'll see you in the next one. Peace out.